Hello and welcome to lesson 7.3 on rational functions with oblique asymptotes. So, last time we were talking about rational functions in general form, and we're still talking about that. So, a general polynomial, p of x over q of x, where both of those are polynomials, is a general form of a rational function. And we talked about this case where if the degree of the numerator was higher than the denominator, right? So like if you said like x cubed plus 2x plus 1, something like that. And I had that divided by like x squared minus 4, right? If this happens, because we talked about growth rate last time, cubic grows faster than quadratic, and so it outpaces it, which means the function's going to grow, right? So its end behavior doesn't stay constant, right? Because when the degrees are equal, it flatlines. If the degree on bottom is bigger, it also flatlines. In one case, it goes to 0. The other is the ratio of coefficients, right? But when the degree is higher, your function is going to continue to grow towards infinity or possibly negative infinity. But it's still going to follow an asymptotic behavior. Even though it's not horizontal, there's still going to be a line which predicts where the graph is going. Yeah? And that's what we're kind of investigating today. So a few specifics to kind of get out of the way. We're going to talk about this word oblique, okay? So first of all, what does oblique mean? It says the word oblique means neither parallel nor perpendicular. I mean, if I had an x-axis here and I had a y-axis here, then parallel, of course, would be a horizontal line, and perpendicular to the x-axis would be a vertical line, right? That's vertical and horizontal asymptotes. So what does it mean to be not parallel or perpendicular? Well, it means to be at some angle, right? It means to be just positioned in such a way. I mean, it could be that, it could be this. The steepness doesn't really matter, nor the direction, so long as it's not perpendicular or parallel. You can just call these slant asymptotes because that's what they are. They're at a slant. But I mean, I like oblique. It's just it's a new word, right? Expand our math vocabulary. It's a good word. Now, something to note. When do you have a slant asymptote? Well, it does occur when the degree of the top is greater than the bottom. So that's true. If the top is more, this is going to happen. But specifically, if the degree of the top is 1 more than the degree of the denominator. So like the one I just drew, x cubed plus blah, 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 x squared plus blah, 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 blah. Degree on top is 3, degree on bottom is 2. The difference between that is 1. Now, if it's not 1, if it's greater than 1, say x to the 4th and x squared, then you're still going to have quite an interesting asymptote, but it's not going to be a straight line. It's going to be a curvy line, right? This is going to be some sort of curvy line asymptote. We call that curvilinear, yeah? So if it's not oblique, it'll be curvilinear, and we'll get to see a few curvilinear asymptotes in this video. And by the way, curvilinear, it's not really a standard thing to teach in Algebra 2, but, in my just exploration, diving deep into these on a personal inquiry, I found this, and I thought, why don't we study this? This is amazing. We should see this. It's just so wonderful. So, I don't know, maybe you might not find a lot of sources on curvilinear asymptotes. You'll find plenty on slant, but this is going to be interesting talking about that. Anyway, the rules are here. So, you can all that stuff that we did last time, horizontal, vertical, holes, and all that stuff. The way you're going to find a slant asymptote is by using polynomial long division. And I'll get there. I'll explain how that is done. It says polynomial long division. Maybe you can use synthetic division if you know how to use synthetic when it's not monic. Remember that word? Remember monic polynomials? When you say like 1 times x plus 2, right? The leading coefficient is 1. If you know how to do it with non-monic polynomials, you might be able to do synthetic, but we'll just stick with long division in this video. Okay, I've got 3 examples for us to look at, so we're going to start with example 1. And this does take a while, but we'll do fine. Okay. So first thing, you figure out all the features the same way you always have. Yeah, the same way you did in 7.2, exact same stuff. Of course, the first thing we're going to start by doing is, can you guess, factoring. So, I've got to factor this numerator right here, right? What multiplies get -8, +2? Well, let's see, that's going to be x plus 6 and x minus 2. No, what am I? Are you crazy, Mr. Spake? X plus 4 and x minus 2. Is that better? Okay. I'm not insane. Good. So I've got that. On the denominator, I've got 4x plus 8. So I'm going to factor 4 out, GCF, x plus 2. Fantastic. So I fully factored top and bottom. I guess, you know what, why don't I just lasso that answer, pull that right there. How neat. That's nice. Okay, so typical features, are there any holes? Well, remember, a hole happens if I had like x minus 2 over itself. That would create a hole. I don't have x minus 2 over itself. I don't have anything. No common factors between the numerator and denominator, so no holes. X-intercepts, to find that, you set the top equal to 0. So you look at the top numerator, you say, okay, -4 makes that 0, and 2 makes that 0. So I have 2 x-intercepts, one at -4, comma 0, and the other about at 2, 0. So and. Next up is y-intercept. To find a y-intercept, you make x 0. So I can kind of, maybe if I zoom in on here, the way I just kind of cover up this. Well, I didn't mean to highlight. The y-intercept is when x is 0, so I'm just going to cross that out. I'm going to cross this out because those are zeros. I'm going to cross 4x out. That's 0. So I just got -8 over +8. Okay, so y-intercept is going to be 0, comma, -8 over +8 is -1. Nice. Let's plot those. Let's get our -4, 0 point here, 2, 0 here, and y-intercept at 0, -1. Awesome. Okay. Vertical asymptotes. So vertical asymptote makes the bottom 0 denominator. I got 4 times x plus 2. The root of that is going to be -2. All right, -2 makes the bottom denominator 0. So I'm going to just nicely make my vertical asymptote like so. All of that is just from 7.2, right? None of that's new, none of it. What is new is, rather than stopping and saying we have no horizontal asymptote, which is true, we don't have horizontal, we will have a slant asymptote. So seeing that the degree is 2 on top and 1 on bottom, the numerator is more, and it differs by 1, so you will have a slant asymptote, or oblique. Make sure you know that word, okay? It's on the test. Oblique, same thing as slant, okay? But how? How do you find that? I mean, it's not like you could just look at it, right? It requires a little bit more effort than some of these other things, not just factoring. But I said earlier you're going to have to use polynomial long division. So here we go. Let's do it. I've got, look at your fraction, right? You're looking at this guy. Take the numerator, x squared plus 2x minus 8. We're going to divide this by 4x plus 8. Okay? Now, ooh, do I have enough space here? Let's move that fella up there just a little bit. Okay. I'll try to write tiny. So, as we know, polynomial long division, hey, if you need to go review that, we got videos on that, right? So you can go look that up if you need to. I'm going to assume you remember. So I need to multiply 4x by something to get x squared. Of course, I have a 4 there, so 4 times 1/4, its reciprocal, makes a coefficient of 1. And of course, x times x is x squared. So that gives me 1/4 x. So I'm going to take 1/4 x and multiply it to 4x and 8. 1/4 x times 4x is x squared. 1/4 x times 8 is 2x. We will subtract this from here. These guys will cross. These guys will cross. I've got a 0 here, which means I'll drop down -8, right? And, well, I say, well, does 4x multiply anything to get -8? Not really, right? I've got an x there. I would need to use division of some sort. So this is the point where we say, okay, this is going to be our remainder, okay? So that's remainder, -8. Of course, how do you write that actually, right? So I've got x squared plus blah, blah, blah. So what this means is x squared. Should I write it over there? I'll write it over there. That's what I'm going to do. I'm going to come over here, and I'm going to say x squared plus 2x minus 8 over 4x minus 8 is equal to 1/4 x. Now, what are you doing with that remainder 8, right? Well, you've got -8 remaining, and it has yet to be evenly divided by 4x plus 8. So we put that so minus 8 over the divisor, 4x minus 8, like so, okay? So this is what you've got, but what is a horizontal asymptote, right? What is it actually? So let's do this in yellow. What happens as you go to infinity, right? Because the idea about a horizontal asymptote is whatever its equation is. If it's horizontal asymptote, it describes end behavior, meaning as I go to infinity, I get really, really close to this number, right? This value. But if it's slanted, it's not quite a number, more so it's a line. It's like it is a growing line that changes. It's just not constant, right? Say, what are you going on about, Mr. Spake? I say, just watch, listen. We're concerned about the end behavior of the function, right? So we're going to look at it at infinity. What happens as x gets big? Well, 1/4 x is just going to kind of become a quarter of whatever number you plug in. If I plug in 1 million, 1/4 of a million is going to be that output, right? So that's kind of simple enough. But what happens to 8 over 4x minus 8? What happens there, right? I'm going to move this up. Let's see. I'm going to move this up here. Okay. Well, as x goes to infinity, and this x gets really big, this term, minus 8 over 4x, well, x gets huge, so huge. You're doing like -8 over 10 million, or even bigger if you like, right? Which is effectively or close enough to 0, right? I mean, -8 over 10 million, minus 8, whatever, is so small. I mean, it's so incredibly tiny. It basically shouldn't even be there, right? It is that gap that's kind of negligible, right? It's this tiny distance that doesn't matter. So where are you going? As x goes to infinity, 1/4 x minus blah, blah, blah goes to 1/4 x. Essentially, that remainder part doesn't matter. Yeah, that's all that means. Our slant asymptote is y equals 1/4 x. That's it. That remainder part, when you put the 8 over that thing grows so big at infinity, it's so tiny, it's 0, basically. So the behavior is mostly following 1/4 x, very closely following 1/4 x, okay? And so that's going to be our slant asymptote. Now, how do you draw such a thing? Well, let's see here. I'm going to start at the origin, and I'm going to use like little dashes, right? So up 1 over 4, about right there. Notice I'm using really tiny points like this. Down 1 over 4, it's about right here. But that's not 4. What is... Oh, sorry. That's negative 4. There we go. Then down 1, back 4, about right there. Okay. So I'm going to try my best to make a straight line. Now look, when you do this on the exam, is it going to be perfect? I understand that the answer is yes, Mr. Spake, it's going to be perfect. I am going to be flawless on the exam for you. Say, I know, thank you. But if it's not perfect, then you get a 0. Now, if it's not perfect, it's okay. Okay, I know you're eyeballing this. If it looks like 1/4, you're going to be fine. Okay, now, if you just get silly, if you just say, oh, well, what if it's that? I say, well, that's just preposterous, right? I say, that's just, no. Don't do that, okay? Try your best. Make sure it's a pretty accurate straight line. Okay, I mean, that's it, really. That's the video. Haha, go have fun, kids. No, we'll do some more practice because this takes some time. What do you do from now, though, right? What do you do from here? Like, what is the function doing? Well, is it coming here and then going down and then coming up like this? Is it going up and then up? Is it maybe coming down like this? I mean, I don't know, right? So remember, we need to test around the vertical asymptote. So I have a vertical asymptote at -2. So I'm going to test a little bit to the left of 2, -2 there. Make a sign chart, which means I'm looking at this fella over here. And remember, don't actually calculate this stuff. Just pay attention to quantity and sign. -2.1 plus 4. This guy, right? -2.1 plus 4. That's positive. -2.1 minus 2. That's going to be negative. -2.1 plus 2. That's going to be just slightly negative. So negative, positive, negative yields a net positive. Yeah? So on the left side of the vertical asymptote, you're going to be going up towards 0. You know what? I'm going to do this in blue. I'm going to do this in blue because I like to. Okay? Just so that it's not like kind of hard on the eyes, you know? It's a lot of red I've already got on the paper. So it's heading up towards positive infinity there. And then down here, I'm going to follow the slant asymptote. It's going to get closer and closer and closer to the line 1/4 x. Nice. Let's now do the right side of the asymptote. X is going to be -1.9. So again, I'm just plugging it into this, -1.9 plus 4, -1.9 minus 2, -1.9 plus 2. The sign chart on that is going to be positive, negative, positive, which ultimately comes out to negative, right? So, and you know what? Let's erase these points, put them in blue. I had it 0, -1, and 2, 0. So it's going to be coming down from here, which is kind of what you would expect in this, right? For the most part, it's going to alternate between positive and negative infinity, but there are going to be instances where it doesn't, you know? And that's my curve. How awesome is that? That's just amazing. I love that. Okay. Boop. Boop, boop. I'm just admiring it. It's just such a nice graph, right? Let's verify that our answer is correct here. You can type this into Desmos. X squared plus 2x minus 8. Let's do that. X squared minus 2x minus 8. And I already forgot the other one. I think it was plus 8, wasn't it? How is it? Wait, hold on. I'm tripping. Plus 2x. Oh, silly. Okay. That's I thought something was awry. plus. What? Hello? Oh, it's plus 8 on bottom. I'm so sorry, guys. Oh, and this is the video you have to watch while I'm gone. Me and my flaws, my imperfections. Okay. That's the graph we got, right? Is that what we graphed? I mean, yeah. 0, -1, -4, and 2. Looks perfect. Is the slant asymptote 1/4 x? There's 1/4 x. Hey, look at that. Pretty nice, I'd say. Right? You could see that it gets closer and closer and closer to that line, right? On the end behavior, that's where I'm going. I'm approaching the line 1/4 x. Awesome. Okay, here's the thing. If you got that, you got that. You can stop now if you think you're ready for the homework. But I do have two very interesting examples to talk about here. Let's kind of leave it up to you, yeah? What example 1 is the mandatory requirement for the test. Example 2 and example 3, well, I just can't help myself, guys. It's just too cool, right? I just have to. So I do encourage that you follow along and keep watching. But hey, if you think you got it, give the homework a try. Have fun with it. But I really want you to see example 3, so please stick around, or at least skip to that one. Okay. Example 2. So this one is pretty much the same thing as we just did. It just has a little bit more complicated factoring, right? It's factoring a cubic, so you have to remember how to do that. Let's put this in yellow. So if you have x cubed minus 2x squared minus x plus 2, sorry for the burp, just had my Raising Cane's for dinner. $16 for the Caniac. Are you kidding me? It's ridiculous. At least I get an extra piece of toast. So let's do grouping. I'm going to group these two, and I'm going to group these two plus -x plus 2. And I take out GCF, x squared, x minus 2. And I'll take out a -1 here. That way the coefficient on the leading coefficient is positive, and that these two match. And by grouping, I'll find that I get x squared minus 1 times x minus 2. But hey, x squared minus 1 is the difference of squares, so it's x plus 1, x minus 1, x minus 2. Yeah, factoring. Woo! Don't forget that, guys. You literally can't. If you think you can get through pre-cal or calculus without that as your standard, as your bread and butter, I do this every day without even thinking, you should. Yeah. Keep working on those factoring skills, okay? I know we didn't have a ton in the last unit, but you need them. You need them. Please trust me. Please trust your teacher who has a degree in applied mathematics and a master's in math education when he says that you need to factor, otherwise you can't get through the class. Okay. Sorry, I was just writing that down. Okay. So I've got this. Yeah. I took a GCF of -4 down from the bottom denominator, and I fully factored this expression. Awesome. I'm great. Well, I'm not great. I'm just mean. I'm good, right? I've factored it. I'm good. Are there holes? No. I don't see any common factors or top or bottom. None. X-intercepts. Okay, well, what makes the top 0? I've got -1, 0. I've got 1, 0. And I've got 2, 0. Yeah? All coming from the roots of that top polynomial. Yes. Oh, I don't like that. There we go. Oh, I don't like that. I say stop being picky. Now y-intercept. Sorry, I'm taking my time. I should probably hurry up. I'm sorry, guys. I just need to format. My mind's going crazy. I gotta format some stuff. What happened to the plus? Plus. Okay. To do the y-intercept, right, I just cover up all the x's because I'm looking at when x is 0. So gone, 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 gone. I've got 2 over negative 12. That's negative 1/6. So 0, negative 1/6. All right. So you've got 3 x-intercepts. Negative 1, 0. You know what? Yeah, it's just fine. 1, 0. And 2, 0. Man, those are really close together, huh? Vertical asymptotes. This is interesting. Well, your vertical asymptote is going to be whatever makes x squared plus 3 equal to 0. Well, if I subtract 3 on the other side, I get x is plus or minus the square root of negative 3. This is imaginary. And if you were listening last class, which actually it was not quite in the video, but it was presented in class. So I'm sorry if you were absent. That really sucks because you would have missed that because I didn't actually cover that in the video. I did it as a warm-up last class. And that is if you get imaginary roots in the denominator, then you don't have a vertical asymptote. Yeah? The idea behind this is your vertical asymptote, right, is what makes the bottom 0, or that's when it's going to happen. But if you find imaginary roots, then that means no real number makes the denominator 0, means there's no real asymptote. There is no vertical asymptote that's going to exist because the only thing that could make it 0 is imaginary, yeah, which is not a real number, which we don't plot, which is not on the graph. So I don't have a vertical asymptote. Okay, now let's do the slant asymptote. So all that stuff's the same. I don't have a vertical asymptote to draw, but I should have a slant. And I do know it's going to be slant because that's a 3 and that's a 2. The difference is 1 higher on the top. So, okay, I can't remember the polynomial. So we're going to do x cubed minus 2x squared minus x plus 2. And we're going to divide this nice little fella by negative x squared minus 12. Okay. So, let's see. Negative 4x squared times what is positive 1x cubed? Well, I know I'm going to need to multiply negative 4 by negative 1/4 to make it positive 1. That's reciprocal. And I'll make that x, so x squared times x is x cubed. Now, careful with your fractions here. Negative 1/4 x times this, that gets you x cubed. What is negative 1/4 x times negative 12? Make sure you carefully line this up because negative times negative is positive. 1/4 of 12 is 3, and there's only a single x, meaning x to the power 1. Don't write that underneath 2x squared. Be careful there. We'll subtract this. And so the negative 2x squared will drop down. Negative minus 3 is going to be positive 4, or no, I'm sorry, negative 4x. Okay. Now, negative 4x squared times what is negative 2x squared? Well, that's just half. So a positive half, if you multiply that, you'll get negative 2x squared here. Half of negative 12 is negative 6, but oh, good golly, you're going to take negative 6 from the 2. Oh, my goodness. And so you're going to subtract it like this, and that'll be gone, but you'll get negative 4x plus 8. So the remainder is 4x plus 8, negative 4x plus 8, which is what you would put divided by negative 4x squared plus minus 12. But remember, we don't care about you. We don't care about you. Remainder, we don't. Because as x goes to infinity, that remainder goes to 0. It is insignificant. I'm sorry, remainder. I hate to call you that, but you don't matter. So I'm going to shift this down a little bit, which means my slant asymptote is y equals negative 1/4 x plus 1/2. Now, this is going to be a little tricky to graph, okay? And I know you guys are trying, okay? It's fine. It's good. Your slope's negative 1/4, so rise over run there, but your y-intercept is a half. Eek. So let's try, let's say, that's a half. Down 1/1, 2, 3, 4. About right there. So I'm going to kind of shift my iPad. I'm a bit at an advantage here because I can zoom in so close, right? Maybe do it a little bit more. Down 1/1, 2, 3, 4. About right there. So continue out to that point in the distance about. Remember, this is a very rough estimate. It's okay. Up 1/1, 2, 3, 4. About right there. Was that right? Hold on. That's a half. Oh, at a half. Up 1, 2. Sorry, 1, 2, 3, 4. That's where we should be ending. Okay. Oh, guys, I'm so sorry. I'm just trying to make sure this is right. 1, 2, 3, 4. Silly. I'm just trying to. Nice. There it is. Okay. That's about as accurate as I can be for now without wasting a million years of your time. So you've got this asymptote, right? I am going to go ahead and make those points blue so you can really see the curve here. Negative 1, 1, and 2. This is interesting. So I know it's going to come from up here. I don't have a vertical asymptote to guide me, so I'm just kind of taking a stab in the dark. It's probably coming down here and then curving up and over and then kind of staying above the asymptote, I'm thinking. Most likely. I think that's what it looks like, okay? This is a guess. So what do you mean you think, Mr. Spick? You didn't do this already? I mean, I don't know. Maybe. The truth be told, it's a typo. I actually didn't mean this graph to look like this. I wanted it to look nicer. But I'm actually glad I made the mistake because look how unique that is. What a nice graph. Let's plug this in. So, yes, I did make a typo, and that's okay because it led to something more interesting than what I originally intended. And I would call that a successful thing. I would call that a win. We made the problem harder. Was it minus 12? Yeah, it was minus 12. There it is. Oh my gosh. Look at that nice little curve. Something's wrong, though. Yeah, it was minus x plus 2. Minus x plus 2. There it goes. Yeah, that's our curve. That's who we graphed, right? Negative 1. Negative... Oh, did we not plot the y-intercept? Oh, I guess not. Whatever. It's right there. That's fine. It is 1/6, so it's fine. It's negative 1/6. That's what we had. 1, and then 2. I see it just barely goes above the x-axis and then comes back down, right? Notice our our slant asymptote was negative 1/4 x. Oops. By the way, there's a 2 times speed button if I go too slow for you. Negative 1/4 x plus a half. So I'm kind of looking at this. You can see on the left side, it's beneath the asymptote. But right after 2, at the x-intercept 2, the red line goes above the horizontal. and seems to stay there. So it's going to just slightly go above my asymptote, but then kind of follow it above, which is more or less what happened, right? It looked like right at 2. So it looks like it was beneath the line. That's interesting. Until 2. So I think with my sketch, I'm just a hair off. I think this is 1. So I think it maybe, yeah. So it's a little bit more like that, probably. Does that make sense? It's fine. I'm not gonna change it. The sketch is okay. It's fine that it's not super accurate. It's okay. This is the curve, right? The shape I made is what it looks like. So I have a general idea of what the function shape is, and that's the goal. Okay. Last thing to end the video. I just love this. This is just awesome. Why don't you just fall in love with math? So x cubed minus 1 over 2x, right? Let's factor this. X cubed minus 1. What an elegant little guy. Just x cubed minus 1. I don't know if you noticed this. This is a difference of cubes, right? X cubed is perfect cube. So is 1. Oh, it's the best one. It's a minus b times a squared plus ab plus b squared. It's beautiful. It's soap. If you remember, same, opposite, always positive. I'm invoking the difference of cubes identity for factoring, right? So I'm going to actually factor x cubed minus 1 as x minus 1 times x squared plus x plus 1. And I got that using the sum and difference of cubes identity. All divided by 2x. There are no holes because I have no common factors on top and bottom. I have one noticeable x-intercept at 1, 0. Do I have any others? Well, what makes x squared plus x plus 1 equal to 0? And I'll let you think about that for just a moment. It's a quadratic, and two numbers that multiply get 1 and add to get 1? Oh, no such thing exists. So how do you find the roots of a quadratic that is not factorable? You sing a little song. You sing x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I just plug in the numbers using the quadratic formula. It's like a negative 1 plus or minus the square root of 1 minus 4 is negative 3 over 2. This result is imaginary. It is complex. So not a real x-intercept. Not an x-intercept you can plot. So 1, 0 will do. That's the only x-intercept I'm going to have. For the y-intercept, well, I'm actually not going to have one because if I make x 0, well, if I make the denominator 0, that's actually an asymptote. So incidentally, I have a vertical asymptote at x equals 0, which actually means I have no y-intercept. So I'm going to have a vertical asymptote here at 0. Now, let's analyze the slant asymptote on this one, right? Let's see. X cubed minus 1 over 2x. Hold on. Cubed? 1? Yes, no horizontal asymptote. But 3 to 1, the difference is 2, not 1. This is not slant. It is classified curvilinear. Huh? Well, how do I do that? Well, you do it the same way you have been. We're going to use long division, right? So I've got x cubed minus 1. Let's do this in yellow. Just kind of make sure. Let's do x cubed minus 1 We're going to divide this by 2x. Now, this is actually a pretty simple long division. It's over very quickly. 2x times 1/2, 2 times a half gets you 1. X times x squared gets you x cubed. So that makes x cubed. And you subtract that and it's gone. And you get -1, but 2x, it's not a single x, it's just 2x times, that's a remainder, right? But we don't care. We say, I don't care about this, right? You can sort of nix that. You can say, I don't care. So the curvilinear asymptote is y equals 1/2 x squared. What? The asymptote is a quadratic? Huh? Okay, let's make a table. Let's make x and y. So let's plug in zeros. Let's plug in points. 0 goes to 0 because 1/2 of 0 squared, right? 1/2, so square 1 squared is 1, take half of that, it's a half. Plug in 2 squared is 4, half of 4 is 2. Plug in 3 squared is 9, half of 9 is 4.5. 4 squared is 16, half of 16 is 8. So, for my asymptote, I have 0, 0, 1 and a half, 1 with comma half, 2, 2, 3, 4.5, and 4, 8. So what does that look like? Well, it's a parabola asymptote. Or I should probably, more proper grammar would be to call this a parabolic asymptote. So that's one leg. And then another here, here. And I'm just using symmetry to get the other points, right? Something like that. And so I'm going to kind of whoop, whoop, whoop. I'm just being very gentle here because I'm graphing a parabolic asymptote. Is it amazing? Yes, it is amazing. So, what? What does this look like, right? You have it's not a parabola, it's parabolic asymptotically. The end behavior follows the branches of a parabola. Oh, okay. So we're going to test around the vertical asymptote as normal. Vertical asymptote is at 0, so we're going to test -0.1. And I'm just going to do some basic quantitative reasoning here. -0.1 cubed is a tiny negative number. -1 is still negative. Over -0.1 times 2 is going to be negative, so that makes a positive. So that means on the left side of the asymptote, it's going up. So what's going to happen is it's going to be sticking close to this, but at some point, I don't know where, but at some point, it's got to curve towards the asymptote. I am following the branch of the parabola like this. And so I've got that. Whoa, okay. And so let's find the other leg. X is going to be 0.1, means 0.1 cubed is a tiny positive number. -1 becomes negative. And 2 times a positive is positive, so that's a net negative. So I'm going to start way down here, and I'm going to be close to the vertical asymptote for a while, but I'm going to come up and go right through the x-intercept, and then I'm going to follow this asymptote that's on the right here. And so that curve I've graphed in blue is the function. Yeah? That is the function. Oh my gosh. What? That's so interesting. So let's put this in Desmos, verify that we're true. That this is correct. So x cubed minus 1 over 2x. We're going to do that. X cubed minus 1 over 2x. Now, look at that. That's what we drew, isn't it? X-intercept at 1 with all that greatness, right? Look at if you came in Algebra 2 at the start of this year, did you anticipate yourself drawing this, right? Did you see this coming? And look at you now. Look at you graphing such a thing. This is amazing. And you can see that 1/2 x squared, right? That was our asymptote. And I'll make that dotted so we can really see it, make it red. Look, it is following a parabola. That's what it's doing, right? The ends are following a parabola. But that doesn't mean it necessarily is parabolic in shape. It means its end behavior becomes more and more and more like a parabola, but it's doing all sorts of wonky stuff in the middle. And that's our shape. Okay, so this is called curvilinear asymptote, yeah? It's not a straight line. It's just as weird, right? One student asked, what happens if it's a difference of 3? Does that make it a cubic? So look, I'm going to raise this to the power of 4. And so now the difference between the numerator and denominator degrees is 3. So does that mean it's going to be a cubic asymptote? Well, let's change that from x squared to x cubed. Hey, look at that. I mean, come on. That is just so cool. It's just so interesting, right? That its end behavior becomes more and more and more like a cubic, but the function itself, right? I mean, what even is that? This is a very interesting shape. So, all right, everybody. Thank you for watching this video. I hope you enjoyed this as much as I really enjoyed making this. This is what, out of all the lessons in this unit, I mean, this one I think is maybe the most interesting, although I really like lesson 7.2 in class. Doing that in class is probably the most fun, but that's just me. I am a teacher after all. So, of course, I think this stuff is fun, right? But anyway, I hope you enjoyed this. Hope it was helpful. Take it easy, rest well, and I'll see you later.